Hey, good morning, everyone. Let me see our responses in the chat. Let me see how excited are you to be in class this morning, just like I have. It's the fifth day of the DSN free AI classes in every city, cohort 3, Python for data science and machine learning. And today we're going to be wrapping it up on this particular course. It's been an interesting 5 days. On the first day, we were introduced to Python programming. On the second day, we were introduced to the core concept of Python programming, the data structure and the Python control structure. And Wednesday was another awesome session. We were introduced to machine learning proper. We were introduced to the exploratory data analytical part of machine learning. And yesterday we had an awesome session by Hadeju Mobi. Yesterday was another fantastic session. There was a lot to learn. There was a lot to learn yesterday. And today, which is the fifth day, we are going to be rounding the class up with another exciting things to learn. And I'm very, very happy to inform you that we have our facilitator on the call already, Mr. Ewezu, who will be teaching us like a 5-year-old, who will be teaching us like a baby, like a beginner again today. But before we start the class, just few announcements. Like I said, this is the day five, which is the final day for this particular cohort and for this particular course. Remember to always fill your attendance because after this course, after this learning track, we are going to be having what we call our hackathon. I know many of us are asking, oh, when do we get our certificate? Some people have even been part of this program since cohort one, which is data analytics with Excel. Then they move to Power BI, and then they are here. And people are asking already, how do we get our certificate? Where's our certificate? After this learning track, yeah, that should be next week or in the next 2 weeks. We are going to be releasing the project participation for the data analytics track, and we're going to be releasing the hackathon for the machine learning track. So you need to be prepared. You need to go back to your jotters. You need to go back to your notebook. You need to go back to your learning materials to start refreshing your memories about what you learned because the hackathon is going to test what we've been learning. Same with the project participation is going to be testing what we learned during the Microsoft Excel class and the data analytics with Power BI. Yes, this is 11:12 a.m. Nigerian time. Good morning once again, everyone. Good afternoon and good evening from wherever you are joining. It's always a pleasure having everybody here. And I think this is a very good time to pass the microphone to Mr. Ewezu. And yeah, most importantly, I'm very sure many of us would like to share our learning experience. I mean, it's been 5 days. It's time to let people know that, oh, you've actually been learning data science. And you can now be tagged a data scientist, you can now be tagged an AI engineer, you can be tagged machine learning engineer. We're going to be dropping full details on how you can do this. I mean, the important organizations, the important people you can always tag on your post. By the time you want to share your post on Twitter, by the time you want to share your post on LinkedIn, by the time you want to share your post on Facebook, we're going to be releasing a details, I mean, of the companies, the sponsors of this program that you can actually tag to your post to also give you visibility. And you can be rest assured that even at DSN, we are going to be promoting your post. We are going to be retweeting, we are going to be liking because this has been a wonderful learning experience for even me myself. Even me myself. Thank you so much, everyone. I wish us a great learning experience today. Mr. Ewezu, please confirm you can hear me loud and clear. Thank you so
Yeah,
much,
good morning,
Oni.
Bukumi. I can hear you.
Good morning. So Onib is wishing everyone the best in their future endeavors. Onib has been one of the I know Onib because he is always present in the class. I know Onib in this class is always present. Onib has been one of our learner in this class who has been very, very active. And congratulations to you, Onib. This is a good one. This is a good one. Over to you, Mr. Ewezu. Thank you so much.
All right. Um, right. So, good morning, everyone. I hope you can all hear me. I hope you can all hear me. Good morning, everyone. So, today we're on the final day of this really interesting journey. I hope that has been worth your time and you learned a lot. So, as we are in this final wrap today, we're going to talk about regression. So, yeah, I hope. You guys remember in the earlier days when I talked about machine learning, I told you that we had two main types of tasks, supervised and unsupervised. And under supervised, you have classification and regression tasks. So can anyone remind me what regression means? Can anyone? I would love to get your answers. Does anyone know what regression is? Yeah, exactly. Good. Nice one, Onib. Anyone else? All right. So yeah, as you said, yeah, regression is a supervised machine learning technique, that aims to predict a continuous number as its output, Yeah. And what makes it supervised is the fact that during the training phase, it's being given labels. And those labels are in the form of a continuous output, for it to be trained on and stuff. So yeah, that's what regression is. So, yeah, that's cool. So we have different types of regression models, honestly. So we have the linear regression, which is like the simplest form, from the name linear. It tries to model the relationship between your features and your outputs, by using a straight line, from the word line, the word linear is formed, and linear regression tries to describe the relationship between your features and your output in terms of a straight line. So that's what it actually tries to do. And then to capture more complex relationships, you have polynomial regression. And I'm sure you guys know what a polynomial is essentially. The equations like your quadratic, like your cubic, these are all polynomials. So polynomial regression is used to capture more complex patterns. It doesn't assume that the relationship is linear. And why is that important? I mean, when you assume the relationship is linear, you are sort of, how do I put it, limiting like the scope of the relationship. So you are more prone to make errors. Why? Because you assume the relationship is linear and then creating the best linear model you can. But with polynomial, you're assuming that the relationship is complex and you're trying to find the best out of a wider range of options to actually fit your data on. A lot of the times, polynomial tends to be better for more complex patterns, while linear only tends to capture like some simple relationships, And we also have support vectors, we also have decision trees, we also have random forest, The good thing with the random forest, what it does is that it essentially combines several decision tree algorithms, to make predictions. Yeah. So that's how that works. So as we have several classification, we have several regression algorithms. So I think today we're going to look at linear regression. We have to start with baby steps and also, yeah. So as we said earlier, regression is a supervised learning technique that trains algorithms to make predictions in continuous form, and yeah, that's essentially it. So as you can see, we have a plot. So our model actually tries to find the best fit straight line that can model this relationship. As you can see, like in this particular plot, you can see that obvious. So you can see that obviously this plot, you can see the curve. So we can see intuitively that actually to get to plot this the best way we can is actually probably be better to use polynomial regression, because linear regression will not capture all the complex of the relationship between the two variables, but that's by design. And as for this one, you can see that, okay, fine. You can sort of see a straight line here. So linear regression won't be bad. It won't be bad. So yeah, you can tell that from looking at the plots, that linear regression actually better for this one. But for this one, it probably won't perform as well, you know. So yeah. Although like generally speaking, when we're building models, we try to start from simple to more complex models. Why? Because simple models are like easier and faster to train. So I guess starting from linear and then moving on to perhaps polynomial or some other more advanced step won't be a bad idea. So yeah, that's essentially how it goes. So like I said, linear comes from the word line, essentially, and they're trying to find the best fit straight line that models the relationship between your features and your outputs. So when we have our line going upwards from left to right, it's a strong positive relationship. How as you can see, when X increases, Y increases or no. But we have a strong relationship. Why? Because as our X increases, our Y decreases. So that's that. And here there's no clear trend. So there's no relationship here really between these feature and these outputs, you know. So that's actually how, you know, from your plots you can see if a linear model will perform decently enough on the data. And if you can tell that it's going to perform horribly, then I guess you can just try a more complex approach, instead. So yeah, I hope that we're all on the same page and no one is lost. Okay. All right. So, all right. Um, okay, yeah, so I'm sure from mathematics, we all know that the equation of a straight line is y is mx plus b. We should all remember that, from our secondary school days. So m is the slope and b is the intercept. So by the slope, it means like the gradient of the line, essentially. While the intercept means where that line meets the y-axis. So here, this line meets the y-axis at zero, so the intercept is zero. Yeah. This doesn't meet here anywhere. I'm sure if you could start from yeah, but yeah, here it doesn't meet here anywhere. So and as for here, this line meets the y-axis here, so this is the intercept. So yeah, you know, and so there are statistical means of essentially calculating these different parameters. Yeah, and like this is one of such formulas used in statistics to actually calculate these parameters. So yeah, this B1 is actually our gradient, while B0 is our intercept, and X are features essentially, yeah. So this is the expression. You might not necessarily need to know the software because I mean our code does this for us, but just for educational reasons, what happens is that we sort of sum the product of the difference between X, like the actual value of X, and you know the best fit line. I'm just saying for y and y and the average value of y. So we sum the product of their differences and divide by the sum of the difference squared for the x's. So well, yeah, we don't necessarily need to know that because our model does that for us, but this is just how it's done by hand and manually. So we know how to find our slope. Our slope being yeah, this is our slope. Our slope is positive. So, there's a positive relationship between X and Y and stuff. So, yeah, and this is the intercept. So where the line meets the Y axis and stuff. So that's just by the way, that's that. So what we want to do today is that we want to predict um a person's salary. So these are examples of tasks that we can do with linear regression. So we could decide to predict a person's salary from their years of experience, determine glucose level from each of the patient, you know, predicting someone's grades based on total study time, and predicting examination score based on student test scores, and there are other myriad examples. So anything that involves predicting a continuous number using some features can be accomplished using regression. So yeah, that's essentially it. You know. Um. So yeah. So I'm sure you guys were introduced to these libraries, NumPy, Matplotlib, and Pandas. So, as we should know, NumPy is used for like, mathematical, like, forming like mathematical like operations on like you know, data in different form on your own data essentially. Matplotlib is used for making plots, and pandas is used for being able to like manipulate data sets and stuff. So yeah, we're going to need to import these these libraries. So can you guys kindly do that? Yeah. So let's use a simple example. So this is our data, yeah. We are going to create a data set, a big data set for linear regression. Yeah, so can you guys just quickly like create this data so you can all be on the same page? So as you can see, our data set is essentially a nested list. Each element is a list that comprises of two numbers, our x and our y. So yeah, when performing regression, you need your feature and you need your labels. Yeah, and I think and so the first value in each sub list is our x. All the second one is our y. So the data set is fit for us to use for regression. Yeah. So are we all on the same page? So my screen is too small, so should I zoom out? Alright, let me zoom out. Let me zoom. Is this better now? Is this better now? Okay. I should zoom out more. All right. All right. So is it better now? I think the data we're going to use later on is was shared in the chat. But yeah, the one we're using for now is the one in this cell. Just to give you like a quick example, this one. So are we all on the same page? Any other complaints? Are we all good? It's worse scale. Should I zoom in or zoom out? Okay. Okay. Out. Okay. I think this is too much now. Like, come on. So is this okay now? It's 100%. So I hope you guys are fine. This is the best I can do. It is the best I can do. It's 100%. So yeah. So after we created our data, we want to like create it in form of a data frame. You know, because data frames are really pandas makes it really easy to manipulate data. So when you have your data in a list form, making a data frame makes it easier to manipulate and deal with. So this is how you create a data frame. You want pandas as PD, so PD your data frame, your data, and then the names of your columns. You know, yeah. So we do that. We print our data. Yeah. So we also want to know the type of data sets. I think we should come out as pandas data frame. Yeah. You know. So all right. Here we also like tell it to which. Okay. So from our data set, we create a variable x. Okay. Yeah. So we essentially tell it the take all rows and all columns except the last one. That's essentially just this first column, you know. And for y, we tell it to take all rows and the last square one column one is the last is the column that our y is on. So we've created our x and our y variables from our data frame, essentially, yeah. And yeah, so we run that and we can see our data frame, can see the data type is being written. And here what happens, here we printed x and we just know x dot shape. So this is 6 rows and 1 column, you know, which is what we had. We had 1, 2, 3, 4, 5, 6 elements. Yeah. And for y to be the and for y to be the same really. So then we print y, and then our y is so our x was a two-dimensional array. Yeah, all our y is there's a 1D array, so it only has like one number to describe its shape. So and that's six, number of variables essentially. Yeah, so that is the another way we could have done that instead of creating a pandas data frame was we could have transformed our list into a numpy array. Yeah. So we stack the data using numpy the column stack, and then we print the outcome. So this is it. Well, let me see something. Yeah. So we're up. Let me just print data as well so I can see exactly what happened. So, so 4, 6, 1, 2, 4. So what this did was okay, it was able to extract all the elements in each column and put them into separate lists, and then combine those two separate lists into one particular list. So if you observe closely, in our data variable, -1, 1, 2, 4, 6, 7, these are all x's. When we use column stack, they were extracted, and put in their own list, while the y's were also put in their own list. And then both were then put, in a bigger list essentially. Yeah. So that's how column stack works. So our X is the first list in this stack data numpy array. So to access it, we use index 0. You know, we change index to 0. We are using index 0 rather. And to change like its shape, to change it into a two-dimensional array, we use this command. It's just how it works. Instead of specifying the dimensions, once you use the reshape -1, 1, it just figures out the length of the rows and everything. So yeah, you don't have to do that yourself. So that's why that works really well, and why is just it's the last element of this bigger list. So index one, we get our Y essentially. Yeah. So these are two ways of getting our data really from a data set. So now we have our data, we have our features, and we have our labels. Remember, X is our feature, X represents our features, and Y are our labels. So now we have that essentially, yeah. And we can begin to perform our regression. So I'll put any questions. And something that should help to copy and paste the code. The code for which particular part. Yeah. So now we're being our model training, yeah. So there is a library in Python called scikit-learn. It does all things machine learning. It does all things machine learning. So yeah, we are going to make use of it. And in scikit-learn is a module called linear model that has a class called linear regression. Now, this linear regression class is actually the model, you know. So we create an object of that class by creating a variable and assign and initializing it to linear regression. And then remember, these brackets are essential, for it to know that you're creating the object of a class. So after you create your object, to train your model, what do? You simply fit your data to your model object. So now we fit our data. Now we fit our data in a particular way essentially. So what we do when fit accepts fit was is a function that accepts two arguments. You know, our x and our y. So that's what we put. No, we don't just put our data sets, but we actually specify. Okay, this is x and this is y. So that's how fit works essentially. So run this. So it's currently training, and yeah, it's done training essentially. Yeah, it's done training. Yeah. So we're able to like find, remember how our a straight line is y is equals mx plus b. So we're able to extract those characteristics. So our model knows the intercept and knows the slope essentially. So print out the intercept. It's just regressor dot intercept underscore. So we print out, and these are intercepts, and this is our slope. This is slope of our straight line. So I hope that everyone is good. We all follow. So any questions of any sort? Are we all good? All right, I'll copy and paste the codes in the chat. So you guys can run them and see and try for yourself. So okay, alright. So that's option one. So you guys can run that, and if you have any errors, let us know. And option two. Why is my battery dying so fast now? Kilo, why did this one start? It's quite unusual. Yeah. So you guys can run that and let me know what happens. So yeah, so and as for regression.score, like this tells us how well it's sort of like so it's a value that ranges from 0 to 1. It tells us how aligned essentially the model's predictions of y are to the actual values of y. So yeah, and the closer your value is to 1 tells you, the better your model is. So this is one way of actually checking the performance of your regression model on a particular data set. This is one way, yeah, this is one way. But really, in the actual sense, some are actually like building like proper models. We actually divide our data sets into a training set and a validation set, and then train on our training sets. So that means we fit our model on the training set, and then we actually then check its performance on the validation data, because a model should not only perform well on what it was trained on, but also on new data. That's how you can tell how good it is. So I think we'll probably come to that later. Yeah, so I hope so. Anyway, was everyone good? Any errors? Is everything good? Okay, okay. Okay. So are we good? Are we good? Are we good? So guys, are we all good? Any questions? Anything? If I can move on, just let me know if I can move on in the chat. Yeah. 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 All right, good. All right. So also I can go on data creation tab. I'll do that briefly. So this is where we created our data. I'll just copy this and put it in chat really. So that it's on draws back. It's on draws back. So that's the data. It's not defined. Are you sure you imported? Can you copy and paste your code into the chat so you can say exactly what you run? So while you are doing that, I shall move on to yeah. So here we're sort of looking at the correlation essentially between our feature and our outputs essentially. So a positive correlation like basically just tells you that you know as they both increase, one increases, the other increases, and that's what we can see as x increases, y increases. And typically, in finding correlation of a variable with regards to itself, correlation is one. So when you correct X and X is one, Y and Y it's one, So yeah, that's that essentially, and yeah. So yeah, moving on. Just moving on. Just moving on. So here, what we're trying to do, we're trying to see what values of Y. So okay, what we're trying to do is that we're trying to do a plot of the straight line that our model decided on, and like the actual like plots of our variable to actually get a feel of how well it performs. So we've seen it numerically using score, but we also want to see with our eyes. So that's what we're trying to do here. So I have created a variable called ypred, which contains all the predictions, and here I'm making a scatter plot of x and y, and I want the dots to be red, so color red. So that's why that is that. You know. So now, in addition to that, I also want to plot the best fit line that our model decided on. So how do I do that? Yeah, I'll simply plot the x and the y. So our x variables and the y that the model predicted, which we found here, our y pred. So I'll plot that. I'll put a different color so that we can actually see, we can actually distinguish essentially, yeah. So this is title, this X label or Y label, and this is to show our plot. So when you run this, you essentially see, what happens. And so for every value of X, you can sort of see the actual Y and the Y that our model predicted. And you can see that, really, so here our X is -1. This is what was predicted, and this is the actual Y. The gap is not that much. It's not that much, you know, at this particular value of X. This is what you predicted. This is the actual value of Y. It's also not that much. Same for this one. Yeah, the gap is a bit more, but it's still decent. Yeah, the gap is smaller. Here, the gap is just a little bit more. So that the model performs decently well on predicting each point. It performs decently well. So yeah, that's just to show exactly what happened, what our model does. It draws the best fit line, just like how we did in physics back in secondary school. If we did physics, or if we didn't, then just ignore that. But yeah, it draws the best fit line through our plots. So that's essentially what our model does. Um, so let me see what this person wrote. It says from second linear model imports here regressions, regressor, linear regressor, regressor fit. And you got an error from that. Are you sure? Yeah, it's linear regression. You see, the class you import was linear regression. Then you now use the linear regressor class that is non-existent that you did not import from anywhere. So yeah, linear regression must be written here. That's why you're getting that error. So if you correct that, I'm sure you'll be fine. So this is essentially what our model does. This is a visual pictorial view of what our model does. It draws the best fit line. And as you can sort of see, like in the actual sense, it performs okay, but we can see that a straight line is probably not the best way to actually model this particular plot, but it does all right because the distances between the predictions and the actual values are not that much, so it does all right you know so if you are working on a problem that requires like very very good proximity between predicted and actual value, then you can always use a more complex model. You could also even tune your hyperparameters because every model comes with hyperparameters. So if you tune those parameters, you can actually improve performance ever so slightly. Well, given that this problem, you know, it's there's a bit of non-linearity in it, perhaps. So actually using a different model might actually be okay. But you can always experiment and use and change hyperparameters. But I don't think we'll have enough time for that today to actually do that. So We decided to create a new column in our data set, data frame, essentially, which is going to be equals to all our predictions. So here we can actually get a glimpse of the predictions and the actual values. You can actually get a feel of them. And you can see that for some it predicts a value greater than, for some it predicts a value less than. That's how it is, essentially. Yeah. And this metric called the root mean square error, which essentially just calculates the distances between each point and the predicted value. And then it squares that and adds them together. And that's actually how we can quantify the performance of our regression models, using the root mean square error. So the smaller your root mean square error, the better your model is, essentially. You know. So yeah. So we have these new data sets, and we want to sort of plot a bar chart of the actual value of y and the predicted value of y. And that's what we do here. So in our data set, we simply select the two columns y and y hat, and where y hat is our predicted values. We tell the kind of plot we want. We give it the dimension of the plot we want. We want a 16 by 10 plot, which means we want the width to be 16 and the height to be 10 inches. We want it to show major grid lines. So major grid lines are like grid lines that are shown on like whole numbers, 0, 1, 2, 3. You see them there, essentially. I want them to be green, and we specify how we want the lines to be, you know, a straight line, you could specify a broken line, that kind of thing. So that's what that is. Minor is for those smaller demarcations in between these major ones, yeah. And then to show our plots, and this is what we get, essentially. So we can also see, you know, so this is another way of showing us pictorially what our model predicts and what the actual values are, essentially. And we have a label here. So the blue bars are Y, orange are Y, so we can actually see, we can actually compare and contrast. Yeah. So as I was just talking about, actually metrics that we can use to evaluate, but it's one thing to be able to visually see what is going on. You can see that it's not too far from the actual values, but we need to be able to quantify what we can see. And that's why I mentioned the root mean square error. And there are actually other errors as well that we can use, like mean absolute error. So the error in itself is actually different between the actual value and the predicted value. Yeah. And and yeah, our cost function is sum of all the errors from all your predictions, sum all your errors. So now the metrics, different metrics we have for evaluating regression models. We have mean absolute error. So what this is that we find the absolute difference between our actual value and predicted value. Yeah. We sum that for all the points we have in our data, and then we divide by their number. So we're essentially finding the mean of the absolute error, which is how we get the name mean absolute error. Also, then we have the mean squared error. So how this one works is that it finds the difference between the actual value and the predicted values, and then squares them for each point and adds them together. Then divides them by the total number of points. So you have essentially found the mean of the square of the error. So that's how you get the name mean square error. While root mean square is the mean square error, but you then find the square root of that, essentially. So I think when I mentioned root mean square error before, I didn't mention the square root. Sorry, what I described was the mean square error. The root mean square error is the square root of the mean squared error. So you can actually use any of these three. You can use any of these three. But now the thing is, they work in interesting ways. So mean square error, because we're squaring the error, we're going to have larger and larger values. So in situations whereby we want to penalize our model for want to penalize him more than usual for not giving like readings as close to the actual value, you can use a mean square error. Why? Because it will be focused on trying to reduce the mean square error, which is actually a bigger number than mean absolute error. So that's one situation where we can actually do that, you know. So yeah, the how you want to penalize your model also depends on which error function you pick, you know. So yeah, but they all work really fine. They all work really fine. But that's one way we use a mean square error. But we want to penalize our model harshly for not giving the actual output we expect it to give. And we don't have to implement this ourselves manually. There are libraries in Python that we can import this from and actually use, you know. So yeah, I hope we're all clear on that. Any questions? Any questions? Any questions? Any questions? So I hope we're all clear on that. But here we're going to just try to like just do a manual implementation because I mean why not? You know, before we yeah, so at least you know actually like how it's done. So we are going to create like a new data set that comprises only of y and the predicted value y hat. Okay. So the number of data points is going to be the length of that data set, number of rows that data set. Okay. And so I'm going to create a new column called error. And that's going to be the difference between y and y hat essentially. Yeah. And then the cost function is going to be the sum of the absolute error. So this is, you know, a function in Python abs. It just finds the absolutes of something. So if you have a negative number, it writes the positive number or the positive version of it instead. That's what absolute does. So we find the absolutes of all the variables in the error column and then sum them together to get our cost function. You know, and then the mean absolute error is the mean of our cost function. You know, it's a singular number that tells us how well our model performed. So we find the mean by dividing by n, and we have our mean absolute error. So, you know, okay, sorry, I didn't even run this one, so I'll get an error, I'm very sure. Yeah, I got an error. That key doesn't exist. So let me do this. Let me do this. Okay, I haven't run my code in a while. What was the last part I ran? Else is yeah. So all the errors are gone. Yeah, all the errors are gone. Yeah. So we print results and we see our actual values, predicted values, and then the errors all in one data frame. And we can see the cost function, and then we can also see the mean absolute error, you know. And as I said, like, the smaller the number, the better our model performs. And this number is a bit large. It's a bit large. So try to get it to get closer to zero, you know. Yeah. So now this is the more automatic way. So as I mentioned earlier, there are libraries in Python we can use to implement this, so we don't have to, you know, work it out ourselves. So remember the scikit-learn which I mentioned earlier. In scikit-learn, we have a function called metrics inside. We have a package called metrics inside it. So we import metrics, you know, and metrics has different, you know, metrics for evaluating models, both regression and classification. But we want the mean absolute error, mean squared error. So to access them, we just, you know, print metrics don't mean absolute error with underscore between each word. And it's a function. So we then pass in the actual value and the predicted value. We do that for the mean squared as well. And then the root mean squared, we just find the square roots. And then for the root mean square, we find the square roots of that. So the square roots function is actually in numpy. So numpy dot square roots of the mean square error and get our root mean square error. So We do that, and we get our values essentially. Yeah. So as we can see, the difference between the actual values and the predicted values, yeah, it's quite significant. So you can see that our algorithm is not really accurate. You know, and so in machine learning, really, to have to create the best model possible, you need a couple of things. More you need a lot of data. And we don't use a small data set. We use just like 6 points, 6 data points to train our model. So that's not really good. Earlier I talked about the fact that linear regression assumes a linear relationship. And that is not the case in a lot of problems because a lot of problems are very complex. You know, linear regression cannot fully capture everything about them. So using linear regression limits what our model tries to do. It only tries to find the best possible linear approximation, but the best answer could be a non-linear one. So that's another issue. Yeah, and four features. So if there's not enough signal between our feature and our values, our model doesn't perform well. So what that means is if the feature doesn't tell us enough if about the output, or there's no yeah, it doesn't tell us enough about the output, then that's another thing that could cause our model to actually perform poorly. But we actually found correlation. It was actually like 0.94 or something. It was reasonably high. So it's not the correlation. The feature tells us enough, but we just simply use enough data. And we also assumed that it was linear. So those are the things that actually like brought us down essentially and caused our performance to be this low. So any questions thus far? Are we all good? Are we all good? So someone says, how can we determine the best evaluation method to check the performance of our model? That's a very good question. So as I mentioned earlier, so our model will work by trying to minimize a cost function, yeah? So how we want to penalize our model depends is what this thing is something that actually like determines what metric we want to use. So okay, fine, generally speaking, actually, so you have metrics for classification, metrics for regression. So for classification, we have the accuracy, we have the prediction, we have recall, we have Econ score. Or for regression, we have these ones. So as I mentioned earlier, when you want to analyze your model a lot for the parameters between um, the actual value and predicted value, we tend to use the mean square error because the mean square error squares the error. So it makes the error bigger, you know. And when you're trying to minimize a bigger number, our model essentially, simplest way to explain is that our model essentially works harder to get that number to be small, you know. So when we want to penalize it really like a lot, you can be using the mean square error, that's a good idea. But when we don't need super accurate or super close enough predictions, we can use the mean absolute error, you know. It just tells us the absolute error between the predicted value and then the actual value. So I hope that's understood. Yeah, I think I talked about the mean square error, but I didn't talk about the root mean square. So let me just do a simple analogy. So let's say we have an error of 4, like a normal error of 4. From a scholar to have 16. If you have an error of 8 between a different like set of data points, when we square we have 64. So if you notice something, root mean square penalizes larger errors more than smaller errors because it gives larger errors bigger values. So it's the mean square error actually gets your model to try to improve the perform to try to like improve the performance on those larger errors. But when we want our model to sort of like treat all errors sort of the same, don't attach importance to bigger ones or smaller ones. The root mean square is good because the root mean square find the square root of those errors. So it sort of reduces them, you know. So it yeah reduces them. So our model treats all errors equally, both big and small essentially. So that's a good use of the root mean square. When we want our model to treat all errors equally, all the mean square error, when you want our model to focus on correcting very large errors. So I hope you catch my drift, you know. All the main natural error is just it's just a simple, easy to understand error, you know. It's just that when you want an error that's very easy to understand. So for example, let's say okay, for example, to explain that better, when we say the mean absolute error is 0.8, what we're saying is that on average, the difference between the actual value and our model's value is 0.8. So if you want an error, it's very easy to interpret. You use the mean absolute error. For the mean square error, when we want to penalize larger errors, we use the mean square error, you know, essentially. And then we use the root mean square error to be able to treat all errors equally, whether large or small. So I hope that's understood. Is anyone confused? Do you have any questions? I hope that's understood. I hope that's understood because the metric you decide to use to evaluate your model, you know, is really important. It's really important. It's really important. It's determined by the, you know, what how you want your model to behave essentially. So yeah, knowing which error to use and when is actually really important. So I hope that's understood. Not clear enough to you. Okay. Let me explain once again. So the mean absolute error is a very straightforward error. Okay. What it tells us the average error. So essentially the average difference between the value our models predict and the actual value. That's what the mean absolute error tells us. It's very easy to interpret and it minimizes the impact of outliers. Yeah. So now the mean squared error, how this one works essentially is, no, I used an example earlier. I said, let's say for one data point, we have an error of 2. When we square that, you have 4. Let's say for another data point, you have an error of 8. When we square that, you have 64. So we have 64 and we have 4. So the mean square error, what we are telling our model to do is to try to always is to focus more on reducing very large errors. That's what we're actually telling it to do. Yeah, to reduce very large errors. Yeah, and for the root mean square error, we find the square root, so the model doesn't penalize bigger errors more than smaller errors. It treats all errors equally, essentially. So the root mean square error treats like all errors equally. It doesn't want outliers to influence our model. The mean square error, it treats it wants our model to focus on solving large errors. And large errors are very common when dealing with outliers. So we want for the mean square error, we want our model to get better at predicting outliers. With truth mean square error, we have no such preference. We mean absolute error, we want something like easy to understand. If it wants an error metric that's very easy to understand. So that's pretty much it. So I hope that's understood. So it's understood. All right, good. So to retrace one more time, mean absolute error. It's easy to understand, yeah. And it treats the mean squared error also treats all errors the same. But I mean absolute error, it's easy to understand, it treats all errors the same. The mean squared error penalizes larger errors. And larger errors are very common amongst outliers. So it wants your model to perform to predict outliers better. That's what the mean squared error does. Then the rule mean square error, you find the square root of the mean squared error. Okay, fine. You and should just sorry, I mean basically, I mean earlier I said that that square root then makes our model to treat um all types of errors equally. That's not exactly true. What the root mean square error actually the root mean square also penalizes larger errors more. It penalizes out it wants a model to get good on out to get good at understanding outliers also. But the square root then makes the it makes this number easier to understand essentially. So think of RMSC as a more understandable MSC. Both of them want a model to perform better on outliers. Mean absolute error has no such preference. That's pretty much it. So sorry for that error. I've made the clarification, so I hope you understand. You don't have to use these three metrics. You don't have to use all three. And as I said, so let's say you want your model to perform better on outliers. You can use either mean square error or root mean square error. For root mean square error is easier to it's easier to like interpret. The output is easier to interpret. So you can use root mean square error if you want your model to perform very well on outliers. But if you have no such, if you do not want that, then the mean absolute error is fine. So I hope that's understood. I hope that's understood, Hussein, and I hope everyone understands. Okay, good. All right. So I think we can quickly work on this. Let me see. Let me see. Let me see. Can you work on three? So are there any questions? I think are there any questions? This is a very good question. Is it possible to check for linearity? before going ahead with the linear since the assumption. Okay, that's true. So the easy way actually, Phoebe, is to just do a scatter plot. That's the easy way. But that might not always be feasible. How? So scatter plots are best for like when you have like just two dimensions. So if you have like a single feature and a single output, you cannot just do a scatter plot and then see, But as for a more methodical way to that's the simplest way to actually check for linearity. That's the simplest way. Actually, just doing a scatter plot is the simplest way. The simplest way. But like also a rule of thumb really is that the more features you have, the less likely it is that your that the relationship is linear. That's just a simple rule of thumb. So when you can do a scatter plot to just look at it, you can do that. But also just bear in mind that the more features you have, the less likely it is the relationship is linear between the input and the output. So yeah. All right. So I'll move on to plus three. Here we have an assignment that I would like you guys to do by yourselves. My colleagues get you with regards to that. Yeah. So as for now, let me move on to unsupervised learning. So can any of you remind me what unsupervised learning means? Okay. Oh, that's a question. It's not because you should the outliers. Well, there could be certain situations where you actually want to predict outliers really well. Okay, so let me give an example. Let's say you want to hmm, predict the prevalence of a disease, essentially, in human beings, even certain feature. So, yeah, and your data set consists of, you know, healthy, yes, I represent some healthy humans and some people who are not healthy, and, given that usually, like in a certain population, I mean, fewer people are going to be sick. So in that data, your outliers are probably going to be people who are not feeling well, so. And if your model was trying to predict if a person is sick, you actually want it to be better predicting outliers. So that's actually one example of when keeping outliers might be good. Although that problem is more classification based than regression based anyway. Well, that's an example of when you actually want your model to get better predicting outliers and not just remove outliers. So that's one example. You know. Another example using a regression case could be, let's say you want to predict the scores of students. And what you have in mind is that you want to be able to know which students in your class are really, really good. Naturally, fewer students are going to have very high scores. So if you want your model to be able to predict which students are the best performers, they are going to need those outliers. Also, yeah, they want to need those outliers. Like also, like speaking also, like people who fail are probably also like who have really, really bad scores are also going to be like the fewer proportion of the data set of the data set, all things being equal. So you have some outliers, those who are really good students and those who are really bad students. Your two like order them. Keeping your outliers is actually a very good idea. So I hope that answers your question, Hussein. Yeah, exactly. Nice one. Yeah, also supervised mental labor. Yeah, that's good. Exactly, good. Yeah, and Hussein, what we're trying to predict once supervised learning, we're trying to predict clusters. We're trying to group. So yeah, and a cluster is very similar to classification, but the difference is that in classification, you have identified the classes already. How? Because you have given your model the labels of these classes. But in clustering, you don't know what groups you are going to have. You don't know. And you hope the model will be able to find out what these groups are. So that's the difference between clustering and classification. So I hope that's on that's good, you know. So we have different clustering algorithms. You have k-means, you have DB scan, you have hierarchical clustering, you have several, to be honest. I think we also have anomaly detection, so we have several clustering algorithms. But we're going to look at k-means clustering today, you know. That's the one we're going to look at. Yeah. So the k-means clustering, what we're trying to do is that we're trying to cluster a particular number of data sets into a predefined number of clusters. That's what the K represents. The K represents the number of clusters essentially, you know. Yeah. And each cluster revolves around what's called a centroid. A centroid is basically like the center of a cluster essentially. Each cluster revolves around a centroid. So the position of these centroids are really key in actually knowing where our clusters are. So how does K means? So you can see what K means does. You have our data sets, scatter data sets, you can't really notice any patterns. We develop K-means clustering and then it groups all the points into different groups, you're able to group them into different groups. So that's what K-means clustering does for us. So remember, I mentioned that actually we are yeah, the K is actually predefined. So how do we find the best value of K? Well, we'll come to that. We'll come to that in a moment. We'll come to that. Okay, so this is how we actually go about image clustering. We choose a number of clusters. The model select constraints. So it takes random points on the data or like on our plots. Now, yeah, on our plots as centroids. It picks random points as centroids. So now, to assign each data point to a particular centroid or cluster, we measure the distance between each data point and each cluster, and the one that has the smallest distance between and the cluster points is the cluster that data points are assigned to. Okay, yeah. So after we've created our first cluster, we then compute our centroids again. Yeah, and after computing our centroids again, we then reassign our data points to the new clusters that have appeared essentially. And like we keep on doing this sort of over and over again until our clusters no longer change. So that's how we know when to stop essentially. So that's how k-means clustering works. And do you guys have any questions? Okay, yeah, James. Yeah, we'll try to make it available so you guys can look at it. My colleagues will probably handle that. Yeah. So does anyone have any questions? Are we all good? So any questions? Any questions? Um, all right, since there are no questions, I'm going to move on. Seems we all understand. Yes. Moving on to how we know the right number of clusters to pick. Right. So there is a particular metric that we use. It's called the within cluster sum of squares. It's yeah, that's the metric we use to know what number of clusters we should settle on. Essentially, and this is really how it works. So how it works is that it calculates the distance between okay, so in a particular sense, it calculates the distance between each point. Okay, so let's take a particular data point, and let's say we have three clusters in our data. So for each data point, it finds the score of the distance between each and each cluster. So for a point P, it finds distance between it and cluster one and squares that, cluster two and squares that, cluster three and squares that. And it does the same for every other point in our data. And after doing that, it adds so all the distances between points and cluster ones, rather square distances between points and cluster ones are added together. All the square distances between points and cluster two added together. And all the square distances between data points and cluster three are added together. That's how we get our within cluster sum of square. So I'll say that one more time. This metric is gotten by essentially calculating the square of the distance between a point and all the clusters that exist. So after it then does that for one point, it does that for all the other points in our data sets. And then all the distances between each point and cluster one added together, square distances added together. All the square distances between each point and cluster two added together, and same for cluster three, because in this case, we choose three as our key. So that is how this metric is actually determined, essentially. So yeah, essentially. Yeah. So how do we use this metric? So how we use this metric is we do something called the elbow method. So what we do is that for varying numbers of clusters, we calculate this metric. And so yeah, we have for set for a large number for a couple of number of clusters, even for 10 clusters. So how we then know the one that has the optimal number of clusters is this. So you notice that between cluster one and two, there's a very steep change in the metric, and the same between two and three. And from between three and four, the change is it's very gentle. The slope is very gentle. It's a very minimal change. And that is how we know that three is the optimal cluster. Why? Before it, we see massive improvements in the metric because the smaller the metric, the better. So we see massive improvements in the metric because the metric reduces rapidly. And after it, the reductions are very, very small. That's how we know that three is the best. And this graph sort of forms an elbow at three. So that's why it's called the elbow method. It forms an elbow at the optimal number of clusters. So I hope that's understood. So I hope that's understood. So now getting to the code, you need to import all our libraries, NumPy, Matplotlib, Pandas, and Seaborn. Seaborn is used for visualization, just like Matplotlib. So yeah, we import this, run. So I believe the data has been shared in the chat with you guys. What we are trying to do today is we're trying to sort of analyze the spending behavior of customers at a particular supermarket. So our data set essentially contains data about the customers and their spending. So the features in our data are the customer ID, their age, their gender, their income, and their spending score. So how the spending score works is that the closer the spending score gets to 100, the more the customer spends. So yeah, that's essentially what that is. Okay. I see lots of people in the chats. Or sure. Okay, that because been resent again. So yeah, I think it should be this second one. That should be the second data set. So yeah, that should be it. So you can easily get that from the chat. So yeah, I just want to see some info about our data set, especially the columns and the type and their data types, and we check for missing values using is node.sum, you know, and there are no missing values, so that's very good. That's very good. All right. So apparently there was a mistake in the original data set. What we have, our gender column was called genre. So you can easily change that using rename. Okay, yeah, that's what it's here. Yeah, genre. I'll print out our column name genre instead of gender. Yeah, so we can rename that using the rename function. Now we have gender. Yeah. So value count essentially shows us the number. Okay, so what value count does is it shows you how many times a particular value appears. So in our gender column, we have to value male and female. So value count shows us how many times each value appears. So you can see that we have more females in our data set than male. So yeah. So now, in this gender column, we have strings, we have words, and computers cannot really understand, cannot really make sense of this. So we have to convert this to a number. We convert this to a number. And we are using label encoder to convert, this to a number. So we import label encoder from pre-processing in scikit-learn, and we just fit the values in the gender column to label encoder, and we assign the new value to that column. So yeah. And now we can see that we have 1, 0, we have numbers now. All the males were converted to 1 now, females are converted to 0. So another way you could know which was converted to which was if you do inverse transform. So for example, let's say you want to, yeah, just, you want to know um, what value was assigned to a particular category. I could just find, okay, let me see something. Which should be one year, so I'll put that in list. Yes, I should solve what since that one. There's no necessarily that. How was it written? It wasn't, wasn't it? Um, and yes, it should be how it works. So, but did we do anything else? But I'll come back to that. Investment company meant to work for us to be able to see. Oh, sorry, forgive me. That's not how it works. We are going to convert the number to what to a string. That's how inverse transform works. So we put in the category, we inverse transform, and from there we get what was there before, the string that was there before. That's how inverse transform works. So that's in case you, for some reason, you can't, yeah, that's another way to go about knowing what value was converted to 1 and what value was converted to 0. Yeah. If we do inverse transform for 0, I'm sure we'll see female as well. So, oh, you do inverse transform 0, and yeah, you see female. So that's how that works. Yeah. So we've sort of, we know, let us on EDA, we know the distribution of our gender. We have more females than males. Yeah. And we are want to be a plot. So you symbol to be count plots. And yeah, we can see from our plots, yeah, we have more females than males. Now to get, yeah, we use describe to get like lots of descriptions and statistics about what this topic now. Standard deviation, upper and lower percentile, and we have that. So you can see the mean. Yeah, customer ID elements is normally treated as a number, so these don't really mean anything in the actual sense because it's treating the ID as a number now. So this don't really mean anything. But going to other features like gender, okay, fine. You have 200 things in total. Actually, the count will be the same for all features. After all these, essentially, the number of points in our data set. Yeah, so like the meaning and these things don't mean much for customer ID because customer ID is when it's a number, sure, but it's more of like a number in string form. That's how it should be ideally, not like the regular number, you know. So this is also the meaning of gender, navigation, the max, the maximum age, the mean age, the median age, and the income, maximum income, the mean income, the median income, the minimum income, all this stuff. Interesting statistics and stuff too. So it's sort of like find the correlation of each feature. Let's do a plot of the correlation between each feature in our data. We do a pair plot, you know, and we ignore we started from one because we just ignore customer ID. It's not a particularly relevant feature. It's not really. It's just how we identify a customer, but it doesn't really describe customers, figure one, So it's not really going to be true for our model. So you just like ignore that, you know. Yeah. Any questions? Any questions? Yeah. So that's running. Yeah. So that's running. So you see the features are ranging vertical and you know. So see gender. So gender goes from 0 to 1. So you can see we have more zeros, which are more female than male, and it's the special correlation between other features as well. So taking age and annual income for example, you can say, oh, yeah, we can sort of see that generally as like age increases, your income sort of does increase, but I mean, it's not exactly a perfect correlation. So yeah, you just show us plots for sort of get an idea of how or different features are correlated. So, yeah. So you can see we have a really high concentration of, so this is annual income. We have a really high concentration of high income earners in the middle. You can see these guys here who earn the most, they are in the middle of our plots, our age plots. So you can see that a lot of people that earn really high middle age, essentially, they're middle age because, yeah, they're middle age, really. These are the people who earn the most. Then their ages are in the middle age range. That's something we can get from that. We can also see that spending and earning are more or less uniform for both genders. So how both genders spend are essentially the same. There's not really any huge difference. Um, I don't think that is- So this, I'm going to ask you, shows our income, the vertical shows our gender. So for so zero is female, zero earners. For male, similar good number, but really high income earners. There's not that much of a difference really, and those who earn decent amounts also a similar number, and those who don't earn that much to a similar number. So their incomes are not so different really, yeah. And exactly. So because both genders sort of like spend and earn, is roughly the same, you don't really have to focus more on a particular gender. So gender neutral products, will be a good idea. There's products that appeal to both genders, because there's no really difference in how both genders sort of spend or earn. So those are just some insights you can see from looking at these plots. Yeah. All right. So going ahead, what we decided to do is we just sort of study like annual income and spending really. Yeah. Those are the two features that we actually want to look at. We want to see if want to see how our model will include how people spend based on their income, because that seems to be the most important factor that determines how people spend. Because the agenda is pretty much the same. The age does seem quite important. Yeah, age does seem quite important. You can see actually that yeah, a lot of our high spenders are not particularly old people. Yeah, but like we can see that actually even like really young people like have a good number of people who spend a lot. And then like but then when you come to annual income, you can sort of see a stratification. You can see that okay fine. You can sort of see a stratification really, and like just like generally you know that okay, how a person spends depends a lot more on how much money they have than their age really. So that's just really it essentially. So that's why we decided to look at income and spending. You know, that's pretty much why I'm close because when we look on the plot, you can sort of see identifiable groups when we do our scatter plots. That's pretty data sets. Example that comprises just of small income and spending score. And now we begin to sort of look at our best value of K. All right. So I'm sort of having power issues right now, and my laptop might soon die. So one of my colleagues is getting ready to take over from me. So if I suddenly go on mute, do not be surprised about that. All right. So let's just continue in the meantime. So are there any questions at the moment? Do you have any questions? Any questions? Notebooks are going to be shared if you only they're going to be shared. They're going to be shared. All right, so this is where I take my leave, guys. My colleague is going to take over from me at the moment because I'm unable to continue. So you guys should have fun. He'll join shortly. All right.
Thank you so much, Mr. Ewezu. Please confirm you can hear me. If you can hear me loud and clear, let me see your yes in the chat. Loud and clear. Thank you so much. Thank you so much, Chechuku. Thank you so much, Ewezo, for the feedback. It's been an awesome 2 hours of learning. Oluwatomini said, yes, very well. Monday said loud and clear. Thank you so much, everyone. And yeah, this has been another awesome delivery. This has been an awesome delivery. I think Mr. Iwezu deserves a round of applause and our favorite emoji. Let's celebrate him in the chat. Let's celebrate him in the chat. It's not easy actually to teach. I mean, for some of us that facilitate classes, we know how this thing runs. It's not easy to teach. Not easy to teach, and it's not even about teaching. It's also about when the learners actually get it correctly. I mean, when they really get what you are trying to teach, that's even the joy of it all. And he has delivered. Yes, Mr. Iwezu has delivered. Thank you so much for taking us through today. And I think Adejumobi too was on the call for some minutes. They've done really well. They've done really well. Thank you so much. So very quickly, I'll be making few announcements. But before that, for some of us that joined quite early, I told us about the project participation and the hackathon that will be happening. You agree with me that for these free eye classes, we're actually running, let me say, three learning tracks. We have what we call the data analytics with Excel and data analytics with Power BI. These two courses are under data analytics. I mean, once you can master these two courses, you can actually start calling yourself a data analyst. And then we have this learning track, which we are calling the Python for data science and machine learning. And next week again, we are going to be having another learning track called the machine learning with Microsoft Azure. So for some of us that are very interested in deploying some of the apps we build, or you want to use Azure premises, I will highly encourage you to join S3 Cohort also. So these two courses will be under the data science learning track. You have interest in being a data scientist, you have an interest in being an AI engineer, you want to become a machine learning engineer, you want to do more of research, AI research, then data science learning track is what is best for you. And in the fifth week, which is going to be the Cohort 5, we are going to be doing apps development with Microsoft Power Apps. Apps development with Microsoft. So this is for anybody that is interested in building business apps, or you want to automate some of the things that you do in your day-to-day activity. Please confirm you can still hear me in the chat room. Please confirm you can still hear me in the chat room. So I can see some questions that, oh, can you drop the note? Okay, thank you so much, Olubumi. Thank you so much, loud and clear. Yes. So as regards the learning content, we may not be able to share this due to some reasons, but you can be rest assured that once we end this meeting, this recording will be made available on our DSN YouTube channel. This is actually where we record this session, such that you can always fall back on the recording, because we may not really be able to share you the learning resources used by the facilitators. So once I end this session, you can always get on the DSN YouTube channel to get back on wherever you have missed. So like I was saying, we're going to be having our hackathon and project participation. So project participation will be for those that are taking data analytics track, while hackathon will be for those that are taking the data science learning track. And then apps development also, they are going to be building an app. All this just to test what you've been learning. So before I make the next announcement, I'm going to be sharing my screen now. Let me know when you see my screen. Please confirm you can see my screen, and what can you see on my screen? So I'm going to the chat now. Abari. Amazing, Abari. Oh, someone is a bonjour. So what platform are you saying this? Can you say the name of the platform? Zindi. Thank you so much, Henry. Oh, somebody is saying I can't see your screen. That's Asham. Asham. So it's going to be your internet, because others can see my screen. So I will advise you to quickly log out and join again. Yes, Ado says Zindi. So quickly log out and join again, because I want to explain how Zindi works. So if this is your first time or let me say, if you've heard about Zindi before, let me see your yes, yes, yes in the chat. If you've heard about Zindi or you've heard about Kaggle, let me see your yes in the chat. Ahmed said yes. Cool. Henry said yes. Oh, David said no. Monday said no also. Yeah, that's why I'm sharing my screen so that I can do a quick brief on Zindi. So we have Zindi and Kaggle, and these two platforms are the play we call it the data scientist playground, because this is where you come to actually test your data science prowess. I mean, you've been learning about exploratory data analysis, you've been learning about building models, you've been learning about algorithms. So Zindi is the right platform. Kaggle, they are the two best platform for data science where they come around to play. For the data analytics guy, after you are done building your dashboard, you are sharing your report with stakeholder, it ends there. But for a data scientist, the main thing, or let me say, the end goal of being a data scientist is to be able to provide solutions. Same thing with the data analytics guys. So you make predictions, you make this or what will happen in the next few days. You want to do churn analysis, you want to do fraud detection. So Zindi is the best platform, and Kaggle where you can actually come to showcase your data science prowess. And I'm also excited to inform you that Zindi is actually a DSM partner. I mean, Zindi has been they've been our day one. They've been with DSN from the day one. You can see DSN logo. You can see Microsoft, Google, DeepMind, NVIDIA, EY, InstaDeep, FOSIO, and then the data science Nigeria, because we've always been partnering with them. So for you to get on Zindi, all you need to do is to type Zindi, or you just do a Google search of Zindi. Then you create your account. You click on the first link that you are seeing. So it brings you here where you can now sign in. You can see I'm logged in because I already have an account. Yeah, so that's why I'm here already. So you can see that so Zindi is actually like an African platform. It's more accessible to Africans, but it's also global, but it's more accessible to Africans. That's why you can see Abari, you can see Pele, you can see Hausa, you can see Bonjour, you can see all these relatable languages. So and once you get on Zindi, all you need to do is to click on the compete. So once you get to the compete, you see hackathons, you see competitions that you can actually participate in. And for some hackathons, for some competitions, they're actually for free, while for some hackathons and some competitions, they are paid. I mean, you get a tangible reward. You can see 10,000 USD, you can see 6,500 USD, you can see 5,000 USD dollar. Yes, people make money. I mean, just by building models, by submitting their models, by submitting what they think can happen. So you can see this is wildfire prediction challenge. There's IT. So Zindi post, people come on Zindi to let me say to find solutions to whatever is happening. Yeah. So they come on Zindi, they put their problem solution, they put their problem on the platform, and they ask people to provide solutions to it, and they put an amount, they put a tag reward for it. And then you as a data scientist, you go there, you play around, submit your model, and if you are lucky to be on the dashboard, you get your reward for it. So even if you come to hackathons here, like I said, DSN has been a day one partner with Indy. If you search for data science Nigeria, you are going to see some of our hackathons that we've posted over time. Yeah. So this is the recent one we had with a partnership with OOU. You can see DSN AI Bootcamp Qualification Hackathon. You can see Women's Hackathon. You can see DSN AI Club Footer. So even our campus club, we allow them to also participate. I mean, to also organize hackathon by themselves. So even as a community, we've been sharing links on how to join the different community. We have city and campus community. So you can also join this to make sure that you keep your learning intact. So this is Footer that just had an hackathon. I think this was 3 years ago. So you can see. So we have many hackathons that we've actually posted even at DSN, and the hackathon that will be happening also in the next 2 weeks, if not next week, will be on Zindi. So I will highly encourage everybody to familiarize themselves after this class. Go on Zindi, familiarize yourself with the platform. And we're also going to be making it easy for everyone. We are going to do a detailed video on how you can make your submissions and be on the leaderboard. Let me see if I can open some of our leaderboard. Yes. So this is how the leaderboard looks like. So you see the data, you see the full description of the problem. Yeah. And then you download the data set, and then you start doing your data science thing. So you see, this is so we also make sure to put, this is how we are going to evaluate, so that you are not just building something that is not it. You are not using classification algorithm for a regression algorithm. You are not using clustering algorithm for what is not. So you will make sure that we simplify everything for you to understand on the platform. So we have the evaluation, then the prices, and then the timeline. So you get to also see the timeline. And then after everything, we'll publish the leaderboard. So the leaderboard is where all the participants get to see how they are doing. The leaderboard is where you get to see how you are faring. So sometimes you will wake up in the morning and you will see that, oh, you are no more the first person on the leaderboard. And you can, by the time you use another algorithm, maybe you were using decision forest before to make your submission, and then you use a random you use what do they call this one now? So there is one particular algorithm, XBoost. XBoost is a very good algorithm for I think that when you are doing your classification. So XB is a very good one. If you've been using linear regression, you've been using random forest, and then you use XB, this can actually also boost you on the leaderboard. Can anybody see who is on the night? I mean, can anybody see this person on the night on the leaderboard? If you can see what I'm seeing, drop your answer in the chat. If you can see what I'm seeing on the leaderboard. Adejumobi, thank you so much, Dejita. So that's Adejumobi. So this is where we all start. I mean, this is where we all started. This is how you get to test yourself. Yes, Adejumobi, that's her on the leaderboard. So she participated in the boot camp, and then it's now our turn also. So we are going to be releasing. Did I say yes? Our amiable Adejumobi. Yes, yes, that's her on the leaderboard. So we are going to be releasing the hackathon for everybody that is enrolled in this data science learning track. We are going to be releasing it in the next 2 weeks, if not next week. Yeah, if not next week, we are going to be releasing next week, because we want everybody to also complete the machine learning track with Azure before we release the hackathon. But if it's not going to be released next week, then you can take my word for it that it's going to be released in the next 2 weeks. So there's a lot for us to do. There's a lot for us to do. You need to go back to your learning material. You need to start practicing. You need to start practicing so that you can also see yourself on the leaderboard. So that is Zindy. Like I said, we also have what we call Plagbo. So these two platforms are very good for you to always test your data science prowess at any time. Yeah, and so my colleague has also dropped link. Like I said, when the class started, it's very good for you to share your learning experience. It's been 5 days, and some of us have been present since day one. So it's a very good one to let people know what you are doing. And let me also tell you that the good thing about making posts, writing about your learning experience, is because people can also pick your post and try to engage you for a job or a gig. I mean, you won't even you will just be surprised when they reach out to you. I saw what you did. I saw your learning experience. I saw what you did. I saw your algorithms. I saw this. I saw your experience data analysis, and then they engage you for a gig or a job, and that's where you start with your own making money ability. So it goes on like that. So it's very important that we always share our learning experience. And my colleague has dropped all the tags, I mean, all the organizations, all the names, all the companies that we can always put in our post so that they can help us amplify our post. My colleague has dropped the link, and she will also be dropping it again. And this is also a good time to appreciate Chidima. Chidima has been she has been our dedicated support on this chat, dropping the data set and team tabs, making sure that everybody is carried along. So thank you so much, everyone. So it is day 5, and it is a wrap for this particular cohort. But always know that the conversation continues on the group chat. I mean, our Telegram group. Yes, the screen is blank because I've stopped sharing my screen. So the conversation continues on our Telegram group. If you have any question, we have our dedicated support who will answer your question. Mr. Wezu is on the Telegram, Adejumobi is on the Telegram. Everybody is on Telegram. And even you have your colleagues on the Telegram group, so they can always respond to your question. So if there's anything bothering you and you don't know how to go about it, you can always come to the Telegram group to drop your question. Thank you so much, everyone. Let me quickly go through the chat. Let me quickly go through the chat again if there's any important question I have missed. Sorry, what was the second platform you mentioned? Kaggle. I said Kaggle. So Kaggle, Kaggle. Yeah, so that's the second platform. But we're not going to be using Kaggle for our hackathon. It's just for you to also know another platform where you can always practice. So Dejita is saying a friend is interested in joining the next cohort. How can she register? Dejita, if you are here, it means that you have registered. So you can always share the link with her. The link you use to register is still the same link. The form will always be open till the head of the free class in every city so that we can always invite our friends to also benefit from this wonderful experience. Yeah. So always share the learning link with your friends. The form is open. We are not closing it anytime soon. Yeah. So you can always invite your friends and your family to also um join this wonderful learning experience and also give themselves a competitive edge in the emerging market. Uchechukwu said thanks to DSN team for this great opportunity. It's a player, Uchechukwu. It's always a player. This is what we do at DSN. And Oguntade is also saying thank you very much for the knowledge. You are all welcome. Thank you so much for your kind words. Thank you so much. Um, Fellow learners, thank you so much for joining. This is where we're going to be heading to this session. And see you next week because all of you now are data scientists. So it's very important for you to also come and learn how you can always deploy your model. Yeah, so see you next week and do enjoy the rest of your day. Bye bye, everyone.